Hello everyone, my name is Atharva. I am a third year engineering student at IISMS Institute of Information Technology Pune, and in this video I'll be presenting to you my internship project. So moving on, in this presentation I will be covering the agenda and the overview for my project. Then I'll talk about the end users and the solution. I will briefly talk about how it works, and lastly I'll be covering the wow factors for my implementation. So talking about ADAS systems or advanced driver assistance systems are basically technologies that are meant to enhance and improve the overall driving comfort and safety. Speaking of ADAS systems, specifically in terms of India, they are not very widely implemented, and I would say they are in the nascent stage. So you will mostly see them being implemented as, let's say, rear view parking sensors or proximity sensors. And some high end cars or some high end models, they do have 360-degree cameras and collision detection or collision avoidance. But this is not very developed and not very widely adopted in India yet. And I believe that there is a lot of scope for improvement and innovation in this field. So the problem statement is tackling or rather preventing road accidents caused by drowsy and inattentive drivers. So this is a major concern not only in India but all over the world, and there have been solutions that have been developed for this particular problem, but as of yet they are not very widely implemented or not very adopted overall by the general public. So here are some news articles and some sources to support my argument. Different sources will give you different numbers and different percentages, but the end of the story is that a considerable amount of road accidents are happening because of drowsy and inattentive drivers, and this needs to be looked after. So before we move on to the solution, I would like to briefly talk about the end users. So firstly, we have novice drivers. So basically, people who have just learned recently how to drive, and they may not be able to identify when they're feeling tired or when they should take a break. Secondly, we have the elderly drivers. So as we get older, eventually our mental endurance is reduced. So we are not able to focus for long hours. Third, we have distracted drivers. So basically, drivers who are not exactly drowsy or sleepy, but also they are not fully focused on the road. Then the fourth, we have professional drivers. And I personally believe that these are the most vulnerable ones because let's say you're driving in a city. So, firstly, there's a lot, mostly you will face traffic. You have to stop at every signal. There's a lot of noise and distraction around you. There are pet stays around you. Your average speed is around 30 to 40 kilometers per hour, and you might encounter speed breakers, potholes, and all such things. So you tend to drive slower, and because you know that there is a lot of distraction, you are mentally more aware and you tend to focus more on the road. But now let's say you move on to a highway or a very open empty road. So at highways, firstly, you are driving faster, like around 80 to 100 kilometers per hour. There are very few distractions on the highway. There are no speed breakers, no signals, and fewer vehicles around you. So lesser things to focus on. And eventually, as you're driving, you gradually tend to fall drowsy or fall asleep. And since you are moving at a very high speed, the fatalities and the casualties are also very, dangerous and extreme. So that's why I think professional drivers are more vulnerable. And by professional drivers, I mean long distance drivers. So maybe they could be truck drivers or bus drivers or maybe intercity, interstate cab drivers. And my solution is slightly more catered towards these people or these drivers. So because since I said they are more vulnerable, obviously other people in the end user spectrum will be able to make use of the system. And then we have people with disabilities. So they could be people with cognitive impairments, or maybe people who need visual aid, or people who cannot sit for long hours and drive for long hours. So they can benefit from this system as well. So this is a very basic and high level overview of how this system works. The first step is identifying and detecting a face from the video feed. So here we make use of HAR cascades. HAR cascades are very fast but not very accurate. The reason we don't use the entire video for the machine learning is that if we make use of that, then it will be much slower. So we make use of HAR cascades and we use a quick and easy way of detecting a face. Then we isolate and track the face. And once we have the isolated face, then we pass it on to the machine learning model. So it's a pre-trained model and it will plot landmarks on the face so we can identify the features. And based on these points, we can calculate the distance between individual points and detect or come to a conclusion whether the person is blinking or the person is yawning or the person has fallen asleep. Now, this is my tech stack. So Python was my preferred programming language. DLib is a open source C++ library for facial recognition and facial landmarking. Then we have PyImageSearch. PyImageSearch is a major contributor for Imutils. Imutils is again used for facial feature extraction and facial landmarking. Third, we have OpenCV. So OpenCV is by far the most popular computer vision library for Python, and it can do almost everything like getting the input video, adjusting the parameters for the camera, converting the video into different file formats or different color spaces, adding text on top of video, adding certain shapes on top of video. All of that is taken care by OpenCV. Then we have NumPy. So NumPy mostly I use it for matrix calculations. Then next we have Pushbullet. Pushbullet is an end-to-end free-to-use API solution, and it works very fast. It works like a charm. So I made use of Pushbullet. And lastly, we have SciPy. So SciPy is again used for mathematical calculations. In my project specifically, I used it for calculating the absolute average Euclidean distance for the points. And here's a more detailed look at how these libraries work inside my project. So 60% of the heavy lifting, as I said, is being done by OpenCV. Then HAR cascades are useful for giving us the face in the quickest method possible. Then we are using dlib for plotting points, and lastly we are making use of scipy for the calculations. So here's the code. I will skip this code for now because I'll be diving deeper into it later on in this video. So I'm going to skip this bit. Now coming to the wow factors, I think these factors make my solution unique and different from the other solutions out there. So firstly, my system can run real time at 30 FPS on a single CPU core. So that is very important. So it makes this not very, computationally hungry. And secondly, it does not need GPU support. So let's say you take, for example, TensorFlow or maybe YOLO V5, YOLO V7. All of these are very popular machine learning libraries and models. So they generally need GPU support and not any GPU. They specifically need a CUDA enabled GPU. And these GPUs are very expensive. So that's why I try to not go with that way. And secondly, I have implemented fleet tracking. So let's say you're a person running a delivery business. Maybe you have 100 drivers and 100 different vehicles going on 100 different routes. So how do you track the health status or the attentiveness of each driver, and how do you track where each driver has stopped and so on? So that way, that entire solution has been implemented in the code itself. So at a very basic level though, but it still works. So you can track whenever some particular driver is feeling drowsy or has taken a break. You get a notification on your phone telling you which driver has fallen asleep or which driver is drowsy, on which route he is going, what is his vehicle ID, what is his name, and so on. And thirdly, the last wow factor is sensors. So apart from a basic camera, this does not need any other additional sensors. Even in fact, while testing this, my entire system, I built this, I tested this system on a very basic 720p Logitech webcam. It also worked on my laptop webcam, which was around, I think, 640 pixels. So this does not require a very high quality input video feed. It can work on a very basic bare bones camera. And this cheap camera combined with my single CPU support or single core CPU support, I think this makes my solution very cost effective. And I believe that India is a very, cost driven market. So solutions that are cheaper and easier to produce on a mass scale at a affordable rate tend to get more widely adopted. And considering that this system is designed to be extensively used in all types of vehicles like cars, buses, trucks, and all, making the system cheaper and economically viable is very important, especially for a market like India, I believe. And I think that brings me to the end of this presentation. Now we will move on to the code. Before I move on to the code, I would like to give you a brief visual demonstration of how the backend works to better understand how my project is built. So here I am making use of HAR cascades to detect a face. As you can see, it's not very accurate. It is detecting multiple features. So let me just pick a point here, somewhere around here. Okay, yeah. So here, for some reason, it is thinking that the curtain is also a human face. And this could produce errors. But what I did is, instead of picking up all the features that the Har cascade is returning, I chose to pick up the most largest and the most prominent feature that is present in the video frame. So here it is my face for the most part of the video. And even in a real world scenario, let's say in a car, the camera will always be focused on the driver. So naturally, the driver's face is going to be the largest and the most prominent feature. So once we have the coordinates or the region of interest that we have found for the face, we isolate the coordinates and we track the face. So here you can see this is also done using the Har cascade. So it is accurately tracking my face wherever I move it. And lastly, once we have this tracked face, we pass it on to our machine learning model, and the machine learning model will plot points accordingly. So it goes from 0 to 64. So it gives us a total of 65 facial landmarks. Again, out of these 65 landmarks, we are not interested in all of them. We are only concerned with the eyes because we want to check whether they're open or closed, and same goes for the mouth. So if the eyes are closed, we can say that the person is blinking or he or she has fallen asleep. And if the mouth is open, we can say that the person is yawning. So coming to the code now, I have implemented a very basic text-based logging functionality in this code. So let's say if in case something goes wrong, if there's a bug or there's some mishap or there's an accident or something goes wrong, uh, this code will maintain a log history of whatever operations that happened before. And here we have initialized the API. We have imported the machine learning model right here and R classified here. Then here we have a few variables for fleet management. These can be added or deleted all them when required. So there's just very basic driver ID, vehicle ID, and route ID. And so this is the function that finds our face. So it makes use of a Har classifier. And I fine tuned these particular parameters so that it's more accurate and detects only a single face in the frame instead of detecting multiple faces. And as you can see, it returns a list. So this contains firstly the original video, then it has the subframe or the isolated region of interest of the face of the person, and lastly the coordinates for the face. Then here we calculate the aspect ratio for the eye and the lips, and here we have the absolute Euclidean distance and averages. So all of that number crunching is happening in here in these three functions. And lastly, we have the function to check whether the driver is blinking or yawning. So based on the value we return between the points, so we compare it with the threshold. So if that particular value is lesser than the threshold, then we can say yes, the driver is blinking. Like this one is for the eyes, and for the lips, if the distance between the lips is greater than the yawn threshold, then we can say that the driver is yawning. And again, it returns a value for blink, yawn, and this. The rest of these variables are just for debugging purposes. Here I have initialized a few counters. What I've done is instead of based on a single yawn or based on a single blink, we cannot determine that the driver is sleepy. Sometimes we tend to yawn because we are tired and or maybe our eyes were closed because something went into our eyes, or maybe we wanted to clean our eyes, or whatever the reason may be. So based on a single yawn or a single blink, we cannot decide that. So I have implemented a score-based system. So what happens is that whenever you yawn or you keep your eyes closed for more than a specific time delta, then the score drops. And if the score drops below 70, then we can say for sure that the driver is drowsy and he needs sleep. He or she needs sleep. So that way, we can minimize the amount of false positives. And so here's how the entire system works. Based on this time delta, we calculate temporary yawns and temporary blinks. So uh, if there are too many blinks in the specific time delta, we can say that the eyes have been completely shut, or maybe if the mouth is open for a very long time in the time delta, we can say that the person is yawning. So I'll run this code. I think I'll need to turn off my webcam for this so that it does not interfere with it. Okay, so it's working. It has already started counting my blinks, as you can see. Yeah, it's quite accurate. And right now I have a score of 100, so now I'll pretend to be a sleepy person. It has alerted me once, now I'll yawn. So the score has now dropped. It's at 85, so let's drop it even more. All right. Now it has given me a notification right here. So this is how the free tracking system works. I get a notification whenever the driver starts his or her journey, and whenever the score drops below a certain threshold, and even when the driver stops or the program is exiting, at that time also I get a notification. So the API does not necessarily need to be in the form of a push notification to a mobile device. This API is highly flexible and it can send notifications to any other type of device, whether it be a mobile or a computer or any other type of device. And vice versa, the other device can respond or connect directly with the particular vehicle or the particular driver. And this was originally not a part of my project, and I was not asked to implement this. But later on, I felt that this could be added, and I felt the need to implement this system. So I added it because, like I said before, my implementation is slightly more catered towards long distance drivers and fleet management systems. So otherwise, this will work just fine for any other commercial or non-commercial vehicle or maybe personal use. So the system will work fine for that as well. And with that, I would like to conclude my presentation. I hope I was able to explain everything properly, and I hope that you enjoyed watching this presentation. And yeah, thank you.